And 3 minutes ago isn't really when this story starts. It actually begins 10 full days before anyone on Earth even knew this object existed. And by the very end of this video, you'll understand exactly why two of the most powerful telescopes ever built, James Webb and the Vera Rubin Observatory, both ended up staring at the exact same object without ever planning to. On July 1st, 2025, a survey system called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, spotted something moving through our solar system from a facility in Rio Hurtado, Chile. At first it received a technical label, C/2025N1, but within days astronomers confirmed something remarkable. This object wasn't from our solar system at all. It had come from somewhere else entirely, out of interstellar space, and it was only the third such object ever confirmed in human history. It was given the name 3I/Atlas, and almost immediately, observatories around the world turned their attention toward it. Here's where the story gets genuinely interesting. A few weeks after the official discovery, scientists working with the brand New Vera C. Rubin Observatory in Chile went back through their archived data, just routine housekeeping, checking old test images from a testing phase called science validation. And there it was, sitting quietly in the background of images taken on June 21st, 2025, 10 full days before Atlas ever announced the discovery, was 3I/Atlas. Nobody at Rubin Observatory even knew it was there at the time. The telescope wasn't hunting for interstellar objects that night. It was simply doing calibration work, testing its systems, pointed in a direction that happened purely by chance to include the exact patch of sky where this interstellar visitor was quietly passing through. Rubin continued to accidentally photograph the object all the way through July 20th, 2025, collecting nearly 100 exposures in total, and researchers eventually used 49 of those images in a full scientific study. This makes Rubin Observatory's images among the earliest and highest resolution pictures of 3I/Atlas that exist anywhere on Earth, captured entirely by accident before most of the world even knew the object was real. What did those images actually show? Quite a lot, honestly. Rubin's data revealed that the object had a growing coma, meaning a cloud of gas and dust surrounding its core, and that cloud expanded by more than 50% during the observation window. The object moved closer to the sun and started heating up. That alone is completely normal comet behavior. But there was one detail that genuinely surprised scientists. The object had a dust tail pointing toward the sun instead of away from it. Under normal circumstances, a comet's tail points away from the sun because sunlight physically pushes dust particles backward. A sunward-facing tail is rare, though not unheard of. Researchers have seen a similar effect in at least one other distant comet before. Scientists explain this using something called anisotropic dust emission, essentially meaning the dust wasn't being released evenly in all directions from the object's surface, which can create unusual tail shapes depending on the angle of observation. It's a strange, interesting detail, but it's explainable science, not a mystery with no answer. Before we go further into the chemistry side of the story, it's worth understanding exactly what kind of telescope managed to catch this object completely by accident. The Vera C. Rubin Observatory sits on a mountain called Cerro Pachon in Chile, a location chosen specifically because of its dry air and dark skies, ideal conditions for observing faint objects in deep space. Its main mirror is 4 meters wide, roughly as wide as a tennis court is long, and attached to it is the LSSD camera, the largest digital camera ever built, capable of capturing 200 megapixels in a single image. At the time it photographed 3I/Atlas, this observatory hadn't even officially started its real mission yet. It was still in a testing period called science validation, essentially a dress rehearsal phase where engineers and scientists check every part of the system, the optics, the camera, the software, pipelines before the real 10-year survey begins. During this phase, the telescope is pointed at various patches of sky, simply to test image quality, calibration accuracy, and system reliability, not to hunt for specific objects. That's exactly why nobody realized 3 I/Atlas was sitting inside these test images for weeks after they were actually taken. Researchers only found it later, after the official discovery announcement, when they went back through the archived commissioning data specifically to check whether it might have shown up earlier by coincidence, and it had, hiding quietly in the background of ordinary calibration images, 10 full days before the rest of the world even knew to look for it. Here's the part that shows just how good this discovery process actually was. Rubin captures images across 6 different filters, covering different colors and wavelengths of light, often referred to using the letters U, G, R, I, Z, and Y. Scientists were able to measure the object's position across all of these different bands with a typical precision of about 70 milliarcseconds, an extraordinarily tiny angle when you consider how far away and how faint the object actually was at that point. For comparison, Rubin's general precision on fixed, unmoving background stars is even sharper, closer to just 3 milliarcseconds. So the slightly coarser precision on 3 I/Atlas simply reflects the challenge of tracking something that's actually moving relative to the background sky. This level of detail allowed the research team, led by astronomer Colin Orion Chandler, along with more than 300 other collaborating scientists, to publish a full paper analyzing astrometry, meaning precise position tracking, along with the brightness, shape, and activity levels of the comet, based entirely on this accidental early data. So why does it matter that Rubin and Webb both ended up looking at the exact same object? Because together, they represent 2 completely different but equally powerful ways of studying the universe. Rubin Observatory is built for speed and coverage, scanning huge sections of the sky constantly, which is exactly why it accidentally caught 3 I/Atlas in the first place, purely because it happened to be testing its systems in the right place at the right time. Webb, on the other hand, is built for depth, for extremely detailed, extremely precise observations of one target at a time, which is exactly how it managed to pull apart the comet's chemistry down to individual molecules and isotope ratios. One telescope found the object first, completely by accident. The other telescope figured out what it actually was, where it came from, and roughly how old it is. Neither discovery would mean nearly as much without the other. Rubin gave scientists the earliest possible timeline and detailed shape data. Webb gave scientists the deep chemical proof needed to trace this object's origin back billions of years into the history of our galaxy. The story also says something bigger about where astronomy is heading right now in 2026. The Vera Rubin Observatory officially began its 10-year survey of the sky on June 30th, 2026, called the Legacy Survey of Space and Time. Its entire purpose is to scan the sky repeatedly every few nights for an entire decade, catching exactly these kinds of unexpected objects, asteroids, comets, and rare interstellar visitors, often before anyone else even knows to look for them. The fact that Rubin managed to accidentally photograph an interstellar comet before it was even officially discovered, while it was still in its testing phase, months before its real survey even began, is a genuine preview of what this observatory is going to be capable of once it's fully up and running night after night for the next decade. Scientists expect more interstellar objects to be found over the coming years as this survey continues. And when they are, there's a very real chance Rubin Observatory will be one of the first instruments on Earth to spot them, simply because, unlike almost every telescope before it, it genuinely never stops watching the sky. Meanwhile, James Webb continues doing exactly what it was built to do, taking whatever object gets discovered, wherever it comes from, and breaking its light down into detailed chemical evidence that tells us where it was born and how old it is. This is possible because Webb operates far out in space itself, orbiting roughly 1.5 million kilometers from Earth, away from the heat and light interference of our own planet, allowing its infrared instruments to detect incredibly faint signals that would otherwise be completely lost from telescopes sitting on the ground. Together, these 2 observatories, one constantly scanning wide areas of sky from a mountaintop in Chile, and one capable of incredibly precise, deep analysis from deep space, form a kind of early warning and deep investigation system for anything unusual that passes through our cosmic neighborhood. 3. I/Atlas just happened to be the first major example of these two systems working together, even though nobody actually planned it that way, and it almost certainly will not be the last. Right now, 3. I/Atlas has already passed its closest point to the Sun and to Earth, and it's now moving back out of our solar system, heading off into deep interstellar space again, quietly and permanently. Scientists continued gathering more data as long as the object remained observable, right up until it became extremely faint and much too far away to track effectively, coordinating observations across ground-based telescopes, space telescopes, and even a spacecraft on its way to Jupiter, all working together to squeeze every last bit of usable data out of this brief one-time visit. What we're left with is a genuinely remarkable scientific record, a comet born 10 to 12 billion years ago, drifting quietly through the galaxy for almost the entire history of the universe, before briefly and completely by chance crossing paths with a handful of human-made telescopes on a small, quiet, blue planet long enough for us to photograph it, analyze its chemistry, and calculate roughly how old it actually is before it disappears again for good, likely never to be seen by human eyes or instruments again. That's the real story here, not an alien object, not a terrifying threat, but something arguably far more impressive, direct physical evidence from a completely different corner of our galaxy. Formed before our own solar system even existed, confirmed independently by multiple world-class telescopes, working completely independently of each other, and in Rubin's case, working completely by accident, simply because it happened to be pointed in the right direction on an ordinary test night. It's a genuine reminder that some of the biggest discoveries in science don't come from searching harder. They come from having good enough instruments running often enough that when something rare finally drifts past, you're already there too if you want to keep seeing real, fact-checked breakdowns like this one every single time something genuinely new happens in space. Subscribe now and turn on notifications, because stories like this one are only going to become more common as Rubin Observatory settles into its full 10-year survey. This isn't a one-time curiosity that fades from the news cycle in a week. It's the opening chapter of what promises to be a genuinely new era in how humanity discovers and studies objects passing through our cosmic neighborhood, and 3 I/Atlas is likely just the first of many such visitors we'll get to examine in this kind of depth. Drop a comment and tell me which fact surprised you the most. Was it the accidental discovery, sitting quietly in test images for 10 full days before anyone officially announced the object existed? Was it the strange sunward, pointing tail, defying the usual rule that comet tails point away from the sun? Was it the sheer age of the thing, older than our entire solar system, older than Earth, older than the sun itself, formed in an era of the galaxy that no telescope had ever directly sampled before now? Or was it simply the sheer number of telescopes and spacecraft, Rubin, Webb, Hubble, Spherex, TESS, and even a Jupiter-bound probe called JUICE, that all ended up studying this single object before it finally left our solar system for good? Take a moment to really sit with the scale of what actually happened here. A chunk of ancient ice and dust, formed somewhere between 10 and 12 billion years ago in a distant, long-vanished corner of the early Milky Way, drifted alone through the emptiness of interstellar space for billions of years, never coming close to another star, following a trajectory nobody planned and nobody could have predicted centuries in advance. And then, purely by chance, its path crossed paths with our own small solar system, at the exact moment in history when humanity happened to have some of the most sophisticated telescopes ever built, ready and pointed at the sky. 10 days before anyone officially knew it existed, a brand new observatory testing its calibration systems happened to capture it anyway, almost as if the universe handed us early proof before we even asked for it. None of this required speculation about alien engineering or hidden intentions. The real science, when you actually walk through it step by step, turns out to be more remarkable than any invented mystery could ever be. A natural comet made of the same basic ingredients we've studied in our own solar system for decades, carrying a chemical signature that lets scientists trace its birth back to a time before Earth existed, before the Sun had fully formed, back to an era of galactic history that has never before been directly sampled by any instrument humanity has built. That is what real discovery looks like: patient, careful, cross-checked by independent teams and independent telescopes, and ultimately more astonishing than any fabricated headline could ever make. To be